representation, and another one is a fixed point representation. So today we will be discussing on the floating point representation. All right. So this basically type of representation. Okay, it is basically used to store fractional numbers in memory. Okay, so this type of floating point representation are basically used to represent very large number and very small number precisely, and it is also based on scientific notation. It is just a definition. Okay, what is floating point number? It is basically used to represent very large as well as fractional numbers, and this floating point representation does not have a specific number of digits reserved for the integer part and the fractional part. I'm going to mention one more, that is, does not reserve reserve any does not reserve any specific number of digits reserve, or you can say does not or you can say does not reserve any specific, or you can say like this, does not have any specific number of digits reserved for the integer and fractional part. All right, so this is the definition of your floating point representation. All right, floating point example. If I say example like this, say if you look at number 4, does not have any specific number of digits reserved for integer. Suppose if I have to represent some numbers along with this one, say like that, 66767. Now I can write anything. I can write any large numbers and then fractional point like this, any specific numbers. Okay, it does not reserve the specific number of digits reserved for the integer part as well as for the fractional parts. All right. If it is a fixed point, by the name itself, you can have some idea. If it is a fixed point, then definitely there should be some reserved space for the integer, and that means and for the fractional part. Suppose if I say reserved like this, to say plus maximum and minus 99 is your 99, and minus 9 is the minimum with number of digits for the integer and as well as for fractional part in the fixed point. We will come to that about the fixed point in the later part of the syllabus. But in the case of floating point representation, there is no, specific number of digits reserved. So that is why it is called as it can store very large number as well as very small number. All right, so that is why it is called as a fractional number representation. All right, so we will be talking about the very first. So this is called as a floating point representation. Right now, next is, so how we are going to represent this floating point representation. We will be taking, I'm going to take one slides and I'm going to tell you this one. See, this floating point representation. Just a second, all right, just a second. I got a call, just a second. Okay, let me continue. So the this, as I told you, this floating point numbers is this representation is to it's to represent, is to store your number, very large number as well as very small number as well as fractional numbers. All right, this floating point representation has basically three fields. Okay, it basically has three fields. Okay, basically has three fields. So the very three fields. What are those fields? First field is, you have to note it down. Okay, I will not give you that notes and all. Sign, and the second is significant, and the third significant digits, and the third one is exponent. This floating point representation can be has three fields. First one is your sign, significant digits, and your exponent. Okay, so how we are going to, so let's take an example. Suppose if I take a number like this, 11101.0000110. Suppose if I take a very large numbers, like if I take this numbers, all right, integer as well as fractional numbers. Now, who is this person? Please don't. From next time, you please be on time. All right. So if we have consider this numbers, all right, now these numbers to be represented in the floating point format. How will you represent these numbers, this integer as well as fractional, into floating point representation? How will you represent? All right, so in order to represent in floating point numbers, this binary part, this binary, first you have to note down, there are some steps that you have to follow. Steps number one, we have to, what is the steps? First, the binary number is shifted to the right of the first bit. All right, this is the first step. Second step is the number is multiplied by the correct scaling factor. We will talk about what is scaling factor and all, just to get the same value. All right, these are the number. Third is the number should be in the normalized form. All right, number form. So if you see here, I'll just remove this. All right, I'll keep on removing. So you have to note it down. So let me. So I'll just remove all this. So let me take one more example. All right, so just same example. 111101.10000110. All right, so this is the numbers that need to be represented in the floating point representation. So the first point was the binary number is shifted to the right of the first bit. Right, the binary number is shifted to the right of the first bit. Now, if you look at here, so this is your numbers, which is your fraction number. This is your right side and this is your left side. All right, so what you have to do is that you have to shift to the right of the first bit. If you see here, this is your first bit. All right, this is your first bit. So this point has to be shifted to the first bit. So when you shifted it, you will get the answer like this: 1.1110110000110. All right, all right. And then what we have to do is that the next step is the number is multiplied by the correct scaling factor to get the same value. All right, first, all right. So the number is multiplied. All right, so what we are going to do is that we are going to multiply by the scaling factor. So this is basically a binary number, so we are going to multiply by, so let's then should be into 2, and then you see here how many points we have shifted from 1, 2, 3, 4, 5. Okay, so to bring this point to here, we have shifted 5 positions. So your exponent will be, so it will be, what is this? So it should be in the on the top. That's a power. Okay, it should be in the power of 5. Let me like this. All right. So this actually, what is this? Now you look at here. The number which is before the decimal, that is your 1, is actually 1 is your sign. All right, 1 is your sign. The remaining, all right. Are you all getting it? Yes. Now, the very first digit, the very first bit is your sign. The remaining bits, the significant bits, 1, 1, 1, 0, 1, 1, 1. This check, okay, whether I have written correctly. Okay, 0 is your significant, and 5 is the exponent, and exponent. All right, so this portion, okay, if you see here, this is called as your normalized form. All right, this is when you if I give you a question, if I give you like this, if you convert into this form, then it is called as your normalized form. Now, as I told you that the floating point representation has 3 fields. The 3 field is, first one is your sign, second is your significant, and then is called as your exponent. And this one is called, this whole portion is called as your normalized form. All right. Now, one important points you have to be remember is that the base and the scaling factor, all right, this actually is always fixed as 2. Okay, scaling factor is a fixed one. It is always, it will be always 2, and therefore it does not need to appear explicitly in the machine representation of a floating point numbers. All right, it does not need, it will not see. That's why it is this is fixed. All right, this is fixed. That's why when we started in the first topic, that is as I told you that the represent this one, your floating point has 3 fields. As I told you, actually it is actually it should be 4. Okay, it should be 4. That 4 is your, actually the 4 is your scaling factor, but this does not need to be appeared in the machine representation. So that's why we have only considered only this three part, that is your sign, significant, and exponent. All right, so this is called as your this is how we are going to represent your floating point numbers. All right, now this first bit is your sign, and the string of this string of the bit is called as your significant digits. All right, and it is also known as, this is also known as, so this is also known as mantissa. All right, this is also known as mantissa. All right, so for if we take an example, sign is 1, exponent is 5, and the remaining significant bits are your mantissa. All right, next is, so this is how we are going to represent your floating point numbers. All right, next I'm going to talk about new topic that is called as the IEEE standards. All right, okay, this is the standard, the formats. Okay, when if I the format of representing your floating point numbers. All right, the standard for representing your floating point numbers. Standard for representing your floating point numbers are those numbers number in 32 bits and 64 bits. All right, so this the standard. Okay, so the standard for representing your 32 bits and 64 bits was actually developed by the Institute of Electrical and Electronics Engineer. So that is why it is called as the IEEE standard, referred to as your IEEE. So in some of it is also called as IEEE 754 standards. All right, 754 standards. Now standard is actually the format, or you can call as the format. Okay, a format of representing your 32 bits interact in the form. Suppose if I give you a number like this, if I give you say 14, if I give you a number like this 14, so if I give you a number like this 14, now how will you represent this 14 in 32 bits, or how will you represent this 14 in 62 bits? All right, so there is a particular format, or we can call it the standard, that is called as the IEEE standard. This is basically developed by Institute of Electrical and Electronics Engineer. Institute of Electricals and Electronic Engineering. All right, this is actually in organizations they have developed this standard, the format of representing your numbers, either in 32. If you want to represent in 32 bits, how will you represent? If you want to represent your number in 32, so if I give you like this 67, integers are floating point numbers, right? Now how will you represent this in 32 and then 64? That representation is called as your IEEE 754 standards. This topic is very much important for your exam point of view, as well as for your GATE exam point of view. All right, this is very important. Now, so this, as I told you, your numbers can be represented in 32 bits or 64 bits, right? 64 bits. Now, how will you? So let's do this. So this 32 bits actually is called as your 32 bit is called as your single precision format, and then 42 that is 64 bit is called as your double precision format. All right, now you've got it. So when I ask you, if I say single precision format, then definitely you have to know that it is 32 bits. Means if I give an equation like this, represent this 114.67 in single precision format, then you should know that it is a 32 bits representation. All right, so this is the single precision. This is actually the format. Okay, this is how we are going to represent. So you see here, this whole table. If you see here, it has been, we have three forms, right? Sine, exponent, mantissa. All right. So this 32 bit, this whole is actually your 32 bits. This 32 bit has been divided into three parts. The first one is, which is noted by sign, it is occupy only one bit. Second is your exponent, which is occupied only 8 bit will be there. And then the third one is the string of bits that is called your significant bits, that is actually your mantissa. All right, this is actually your mantissa. And then so there are some mathematical problems that we are going to solve. Before that, we will write down some formula. Okay, there are some formula that you have to know. Okay, so sine is 1 bit, exponent is 8 bit, and mantissa is 23 bit. Okay, so we will not write down some great. All right, just a continuation of single bit. Okay, so just a continuation of a single bit representation. We have to note down that 127 is the unique number. Unique number for 32 bits. 32 bits floating point representation, and it is also known as bias, and it is given by like this. Bias equal to the power of, it should be in the power. Okay, I don't know why it is not working. Okay, let me check. I think it's not working, so let it be. So it is to the power of k minus 1. All right, to the power of k minus 1. That this should be in the power. Okay, this is power. Okay, I'll just throw this. This is in the from 2 to the power k minus 1, in the bracket. After that, we have to put minus 1, where k is the number of bits used to represent the exponent. So thus you can say that thus 3 exponent and bit in 8-bit representation. 8-bit representation. These are all your mathematical terms that you have to know. Okay, additions and 8 exponent. I'm going to write in short form exponent bit in 32-bit representation. This, all right, representation. Now bias equal to 127 for 32-bit. So 2 to the power of 8 minus 1, that is minus 1 is basically 2 to the power of 8. Let me write like this: 8 minus 1 minus 1. What did you get? 2 to the power of 7 minus 1. 7 minus 1. That is, what is the answer? You get 127. Right, that's 127. You will get 127. That is the maximum. That is how we get 127. This is actually the way of this is how we got the 127. And E is the exponent. Okay, E is the exponent. E is the sign exponent. All right, and the value stored in the exponent field is, that is E bar. It is E bar equals to E. That is your scaling factor. But it will be written like this: E plus bias. All right. So this is actually your scaling factor. Right now, you will know. You might find it difficult to understand the problems. Difficult understand the this one, how it comes and all. Difficult to understand the mathematical terms. And this, when we take an example, then definitely it will be very easy. All right. So let me take the first example. Okay. Just remember that this to solve this bias is given by this formula, where k is nothing but the number of bits used to represent the exponent, and and E gas is actually the exponent. This you have to know this formula. E is the scaling plus bias. All right. So let me take the first example. Let me take a very first example. Now, if I take an example like this, so in the exam also, this is gate exam, okay, question paper terms question only, 1259.125 with the base 10, okay, with the base is 10. All right, actually your base should be here only. It should be written with the bracket, and in the this one you have to like this. It will have to write like this. Just a second. I'm sorry. So it will be like this. So it will represent I think it's visible now, represent 1259.125. It should be in the like this in the bracket with the base, say with the base then in single precision format. All right, in single precision format. Now, in single precision format means in 32-bit format. 32-bit format. So if you remember that your first bit is your sign, right? It's your sign, 8-bit is your, what is that, exponent, and then what is that, 23, right? 23, 24, yes, 23 is your mantissa, that is your mantissa, right? Mantissa. So this is how we are going to represent. So this is a question. In the exam, it will be given like this. How will you represent this number in single precision format? Now, the very first thing you have to do is there are certain steps to solve these problems. Okay, step number 1. This is first step. First, you have to convert this number, your decimal number, into binary format. As I told you in the very first, as I asked you in the very beginning of the class, I have asked you about the conversion of the number system. I told you, right? I have asked you, and everybody has said that you already know how to convert and all. So what you have to do is that you have to convert just a decimal. Why this is decimal form? You see here, I have given here in decimal format. The base is 10, so it is a decimal number. So if it is given in hexa, if it is given in octal, you have to convert into binary format. Now the question is given in decimal format. So decimal, you need to convert this decimal into binary form. All right. So how will you convert? So first is convert into binary. All right. So how will you convert? 1259 will have to be converted into binary. So when you convert it, you will get like this: 10011101011. All right. This is the. You can also check. Okay, you can check 1259. How now? What about 0.125? How will you convert? When you convert it, you will get 0.001. You need to multiply, or you should know. Okay, this how I got 0.001. Now next is we have the binary numbers equal to 10011101011. So you just first you write down this number, and then put the point here and write 001. All right, this is the first step. First step is your conversion into binary numbers. So this is the very first step. Next is step number 2. Step number 2 means then what we have to do is that we have to normalize the form, normalize the binary numbers. How will you normalize? That means how will you normalize? You have to bring this point to the very first bit of the numbers. So when you bring it, so 1.00 111011 into what was the scaling factor of fix was 2, as I told you, right? Now how many positions we have shifted? 1 2 3 4 5 6 7 8 9 10. I guess it is 10. 9 10, right? So it will be in the power of base 10. So this is called as your normalized form. All right. Next, the third step. The third step. Step number 3. Step number 3.
Ma'am,
Yeah.
ma'am,
Mm-hmm.
ma'am. Have you not written the part after the decimal?
Have you?
Not written the part after the decimal 001.
Yeah. Here it is. See, this is. You can see, no. You can see my pointer, the mouse.
Yes, yes,
Yeah.
ma'am.
This 10010. It is written here.
No, I mean,
Okay.
during the normalization, when you're normalizing.
No, you don't need. You have to write also. You have to write. I forgot to put.
Mm.
So that what is that? 001. You have to put like this. All right. You have to put like this. This point has to go here in the first bit. So 00 will has to come. All right. So 00 will be added, and it will be like this. I hope it is very simple. All right. It is very simple. Now number 3 is step number 3. Step number 3 is single precision representation. All right, representation. So in single precision here, what is sign here? What is, if you see here, what is the sign? If you see here, you don't get confused. Okay, don't get confused with this point.
One.
See, don't get confused. If you see here in the question, did you find any sign here? Did you find any sign? It's an unsigned. Did you see any negative number here? I don't think. It's everything is positive, right? Are you all getting? So, I made a mistake. I think that's why you all get confused. In the floating point representation, this one, as I told you, right? This is actually, you see here. This is actually your. We will come back. No problem. Just see. Continue with this one. Now you see here. Now coming back to your single representation. What is the sign here? Sign means from the given question. From the given question, you have to see whether the number is positive or negative. Okay, just positive or negative. Did you see positive? If you see that this is are all positive numbers, there is no negative numbers that are, so it is a positive numbers. So your sign will be positive. So it will be 0. Why it is 0? It is because of the given numbers. Right? It is because of the given number. Don't get confused with this one, okay? Don't get confused with the normalized one. So this is actually a sign of 0 means from the given question, and then exponent. Exponent will be how many exponent? Exponent you see here, exponent is basically your 10, right? Exponent is basically your 10. And then mantissa mantissa will be 0, 0, 1, 1, 1, 0, 1, 1, 0, 0, 1. So this is your mantissa. Now bias. Bias for single precision is E dash equal to E plus 127. That is your scaling factors, right? What is E here? E is basically your, so it will give like this. It will give you E is 10. 10 plus 127 is equal to 128. So the 120, no, it's 120, 137. Now 137 with the base of, this is with the base 10, should be in the base 10. With the base 10. Now you have to, in the last form, you have to convert this 137 into, again into binary form, and you will get the answer like this. You get the answer as 100010001 with the base, the base 2, the base 2. With the base 2. Now next is, this is a very lengthy, it's not very lengthy, but it, once you solve it, it's very easy. So number in scaling factor, number in single precision format is given as, so we have to represent this in, again in the in single precision format as, what is the sign? 0, and then what was the exponent? Exponent is 10001001, right? And the mantissa is, you write the mantissa. What was the mantissa? 001, right? So mantissa is given like this: 001110110110001. All right, and then you see here, actually there should be, see, this is actually 8-bit, right? 8-bit, only 8-bit will be allowed. All right, so this is 1 bit, 8-bit, and this is 32-bit, right? So you can count it, right? See, it might be 6, 9, 10, 14. All right, 14, and you can skip it like this because it is all 0, 0. Right, it will be, just skip it. Okay, you can either you write 0, 0, it's also problem, or just continue like this till 32 bits. All right, so this is called as your single precision format. And then one more thing is, still we have time now. Yes, we can continue with the double precision format. Now coming back to this double precision format. So I have made a mistakes. Okay, I made a mistakes here. This one, that one, this is actually not your sign. One is not your sign. Sign is actually the, sign is actually, okay, you see here, this is all a positive numbers, so it will be 0. That's all. All right, so now coming back to your double precision formats. Double precision format, this is 64-bit, right? 64-bit. 64-bit has been classified into 3 parts. Sign is of 1 bit, exponent is 11-bit, and mantissa is 52 bits. Mantissa is 52 bits. Now so we will write some formula. Write formula for the double precision. Mantissa is, sign is 1 bit, right? Exponent is 11, and then mantissa is 52. So this is the, and then exponent is excess to 1023. And then bias is equal to T bar equal to E plus bias. Bias is actually your 1023. 1023. So taking the same example of 1275, okay, 12 or 125. Now taking the same examples, how will you represent that number in double precision? So we will take the same example. Taking the same example, how will you represent them in double precision format? In double precision format. Double precision format, that is in your 64. This is second, okay. Yeah. So this double precision format, right? Certificate or so how will you write? So double precision format, what you have to do, you have to take this same steps, okay, same step that will be here. Then in the third one, that is your double precision format. Double precision formats, 0 positive number that is in given, exponent is also 10. What about the mantissa? Mantissa here. What about bias? Bias is 1023. All right, 1023, and you will get an answer as 1033 with the base 10. All right, 1033 is your E bar. Now, so this is, now you represent this number in, so I hope this is very easy, I guess, right? This is very easy. So you convert this 1033 in this one, and you get answer like this. What you'll get? 10000. How many 0? 4 5 5 6. You just check, okay, 001 with the base 2, with the base, with, with the base 2, with the base 2. All right, with the base 2. Now this is your exponent, new value of your exponent. The mantissa will be remain the same, okay, will remain the same. And then this one, so how will you represent? 0 is your sign, 103 4 5 6 1001, and then your mantissa, what was the mantissa? 0 0 1 1 1 0 1 0 1 1 0 0 1 0 0 0 0. It will continue till 52 bits. Now this is the way of representing your, so S0 is your positive number. This is your exponent, that is after how we got exponent, by using this formula. You get 1033. When you convert into binary, you will get this number, and then the mantissa remains the same. This is called as a single and double precision format. Now if I give you a question like this, if I give you a question, just a second, I'll give you a question. Now so suppose if I give you a question like this, question is given like this, represent 0.0625 with the base 10 in single and double precision format. So how will you convert? All right, how will you convert? The same step, okay, you try this one also, you try this one, and you will get the answer. No, if I, one more example, if I say one represent one, there's one question, 137 Just a second. How will you next is 0.37.1875. 1.75. Now you have to, what you have to do. So if this is question, how will you represent this number in single precision and double precision format? In single and precision format. So what you have to do, so solution will be like this. So what you have to do, it's 307, right? 307 you convert into binary and one in hexadecimal. Okay, so convert this 307 and 18. All right, 1875. Then what you will get, once you convert it, you will get answer as 10011110011 plus 0.0011. Just a second, all right? Just a second, I'm gonna check. Hello? Hello? Ado, ay di nga si Poto Poraktreba, o kano, the message ko no college ng tara halaka ba dugi. Hayeng kumulaki ba yagadra? Yumda Poraktaba, ay kasom da tama ba dugi, yung mama da tanan ba dugi. Adugi nila. Ano nga di. Okay. So let me continue. Okay, so you need to convert this 307 into binary. When you convert it, you will get like this answers, and 1.875 when you convert it, you will get the answer this way. So you will get the answer as 110011.0011. Now you see here in the given question we have minus, right? So we will write as minus. All right. Now next second step. Second step number 2. Step number 2. In the step number 2, we have to normalize this into binary. So when we normalize minus 1.001100110011 into what is it, into 2 to the power of what is, how many points we have shifted? 3 6 7 8. 3 6 7 8 with the base of 8. All right, with the base of 8. Now we will see that the representation of the number in single and precision. All right, now step number 3. Step number 3. Step number 3. Now for the given numbers, what is the sign here? Sign is for the given number, from the given number, S is 1, right? And E is 8, and Mantissa is, and M is 0011 0011 0011. Please correct it, okay, when you solve it. Now bias is equal to single precision is 127. Bias for single precision format is 127. Now solve it and you get, so bias is 8 is 135 with the base 10. When you convert into, you will get 1000011 with the base 2. All right. Now 1 is a sign, 1 0 0 0 0 1 2 3 4, and then the rest of your will be your Mantissa. All right. So this is your single precision. Right, you write the Mantissa also. Mantissa is also 0011 0011 0011, and the rest will be 0 0. Like will be 0 like that. All right, this is a single precision format. Now for the double precision sign is also 1, Exponent is exponent e dash is equal to 1023 plus what is the number, what is the exponent here? Exponent is 8. What is the answer you get? 1031. So when you convert this into, you will get answer as 1 1. This is okay, 3 4 5 6 7 7. I guess it's 7 1 1 2. All right, with the base 2. So, so this is your exponent, right? Sign is your 1. Why we have 1 here? Because it's of, because we in the question it is given as negative numbers, because here it's negative, that is why your sign is negative, sign is 1. So I hope this is very easy, right? So I want so one question I want you to add in your assignment. You solve this one also. You solve this 0.0625. You add this question, okay, in the assignment. Question number I think I have given you 5 or 6 question, right? You add this number, represent 0.0625 in your single precision, just single and double precision, and you submit me by tomorrow 3 o'clock. All right. So when you submit it, you write your name, your enrollment numbers, and when and you have to, I'll give you this one. Submit in me. What you have to do is that you have to write it down. All right, you have to write it down in your papers, take a snapshot and send and make a PDF. If you know how to make a PDF, make a PDF and send as a single file, and a single file in the WhatsApp number before 3 o'clock. All right. So if you find it, so we'll stop here, and tomorrow